All right. So chapter 11, we're getting close to the end. So chapter 11 is a mathematical object called a relation. That's what we want to look at, okay? So here I have the definition, and I put the star by it because I changed it a tiny bit from the book. The book only does the second of the two definitions. But in order to understand it, we need to remember what the heck that notation means. What's that notation? That A with that times symbol and that B. Cartesian product, cross product. Well, yeah. So that's when you make ordered pairs, right? First element comes from A, second element comes from B. Okay. So, all right, so we remember our notation. So we say R is a relation from A to B, and the order matters because your first thing is coming from A, your second thing from B. You know a common example of relations, functions. We'll take stuff from one set that you input and output stuff from a second set. Okay, so functions are a special type of relation. That's actually chapter 12, but we're doing generic relations here. If I only have one set, it goes from the same set to the same set, which often happens with functions, right? Real numbers to real numbers. Okay, then we just say it's a relation on A. All right, so that's our phrasing. Now, notation-wise, we can write this a few different ways. Since the relation is a subset of the Cartesian product, I could say ordered pair AB is an element of R, right? Or in that same vein, I could say maybe some ordered pair CD is not an element of R. All right, but that gets cumbersome and annoying, and we don't like writing it like that. So mathematicians, because they like being concise, came up with another way. And there's a reason for it too. But what we can write, we write A, then capital R, then B. That means the same thing, that the ordered pair AB is in R. A relates R to, or R relates A to B. You actually know some relations that we write like this. For example, equals. That's how we write equals, right? Less than. That's how we write less than. Okay, so you already know some relations we write like that. So, well, I'm gonna look at those later. Okay, if I'm trying to say it's not in R, then I could say A, R with a slash through it, B. That means R does not relate A to B. Okay, there, A, B is not in there. And again, you see that with equals, A not equal B. You see that all the time. You may not see that as much with less than because negating it is so easy, but you will occasionally in a math book see a less than or a greater than symbol with a slash through it, meaning not, okay? So we're gonna use that second notation most of the time, but remember, I'm really talking about a set whose elements are ordered pairs, okay? All right, so here we go, example 1. So X is just the set 1, 2, 3, 4, 5. So that's the entire set I'm considering. Those are the only things in existence according to this relation. So then I just made a bunch of random ordered pairs. That's a relation because it's a subset of X crossed X, right? All my first elements come from X. All my second elements come from X. So it's a relation on X. Now we could say, right, 1 is related to 2, right? What's something in here that, what are two numbers that are not related? According to this relation, so that I can do one with a slash through it. Okay, so 2 is not related to 1, you're right. Okay. All right, And we're going to come back to that. There's space because we're going to come back. But let's look at another one. Example 2. Okay, so here I have a relation S, and it's what are its coordinates coming from? What types of numbers? Integers. Okay, so it's a relation on Z. So here I've written it. It says, okay, I want all ordered pairs that satisfy that equation. Well, you actually know what that equation looks like, right? Y equals absolute value of X. What's that look like if I did real numbers? Yeah, we get this V where the edges of the V have slope 1 and -1, depending which one you look at. If I limit myself to integers, I'm just going to get dots, right, at the points that would be where the integers are. And so on, okay? So according to this, if I look at my picture, 1 is related to 1, and 1 is related to -1. So let me ask a question. Is -1 related to 1? Oh, I'm using R. I should be using S. Sorry, guys. Shame on me. That looks weird, I know, but. So 1 is related to -1, right? Or do I have that backwards? Oh, I got it backwards, don't I? I think you do. Yeah, good catch. Good job. So why don't we just change this question? Or, oh, I'm the wrong color. But still leave space because we're coming back to these. Or 1 related to -1. There we go. Which one of those is true? Yeah, you're right. The first one, because that would be that point, okay, is -1 in the first coordinate, 1 in the second coordinate. Yep. Ooh, yes, okay. So that's another example of a relation. So if I wanted to, I could write S, I could actually write out all, you know, a list that kind of described the ordered pairs by listing with dots, but it's good enough. Let's look at G. So now for G, what types of numbers are making up my coordinates? Real numbers. And I have X greater than Y. So let's draw our coordinate axes. X greater than Y. So I take the line X equals Y, but I need to make it dotted because I'm not allowed to be equal. And if I take stuff on this half, X is bigger than Y. Any point you take on this half, X will be larger than Y. So I'm not even going to try to list, right, those infinitely many, because I could list kind of a nice organized list for the previous one, even though there are infinitely many. But this one, how do you even begin to list all those points that are highlighted? Because it includes stuff like pi, comma, square root of pi, right? How are you going to list everything? All right. So everybody okay with the idea of a relation? It's just set of ordered pairs. Okay, set of ordered pairs. All right. So in order to work with relations, we actually need some properties of them that we can look at. So here we go. Here are 3 properties. And these are the most important ones you'll see typically: reflexive, symmetric, and transitive. Reflexive, symmetric, and transitive. So let's look at these one by one. The relation R is reflexive on A, provided that for each X in A, X is related to itself. Okay, so basically that one is saying everything, I'll write this in tiny. Everything is related to itself. All right, a little too much. Okay, so I have here easy examples. For example, let's think about equals, right? So if I use equals, is it always true that x is equal to x? Yes. I don't care if you're in the reals or the integers or the whatever your numbers you're working with, right? X equals itself, okay? So this is reflexive. All right, what about x less than or equal to x? Is that always true? Yeah, because x still equals itself, right? So this is reflexive. But let's look back at our 3 examples, okay? I guess I'll scroll from bottom up. Example 3. According to that, am I going to get any x I pick, is it going to be related to itself by g? Good, why not? Yeah, this would mean, so this means x greater than x? No, okay? You guys see that in order to be in G and to be related by G, I have to have first coordinate bigger than second. And this one doesn't do that. So this is not reflexive. All right. What about S? Well, so some of them work, right? 0, 0, 1, 1, 2, 2, 3, 3. Those are all here. I have those. So why don't we write it this way? Reflexive question mark? So yeah, so 0 is related to itself. 1 is related to itself. But negatives aren't going to work. I never get like -2 related to -2. Okay. I guess I'll strike through. So not reflexive. So it almost worked, but reflexive says it has to work for every single, x. Okay. Well, let's look at example 1. So reflexive says it has to work for every single thing in my set, which is x. So it works for 5, right? 5 is related to 5, but nothing else. Okay, so yeah, 5 related to 5 works, but 1's not related to 1, 2's not related to 2, 3's not related to 3, 4's not related to 4, so it's definitely not reflexive. Okay. So everybody kind of have a feel for reflexive, what we're saying. Now you do have to be careful. Sometimes sets can pretend to be reflexive. So if I have a set where it's reflexive on everything that or a relation that's reflexive on everything that appears in it, you still got to be careful, because what if it completely left a number out of your original set out, right? So you need to be sure every single number from that original set has to work. Okay, that's reflexive. And back down. Symmetric. So this is an if-then statement. So if X is related to Y, then Y is related to X. That's what we mean by symmetric, okay? So if X isn't related to Y, I don't care if Y is related to X or not, right? It's only if I have some relation between X and Y, then I need to be able to flip it and still keep it true. So let's see what we mean with our easy examples. So if X equals Y, then when I flip it, that'd be Y equals X. What do you think? Yep, that is definitely true. We like equals. What about if X is less than or equal to Y, then Y is less than or equal to X? That's a big no. So equals is symmetric. Less than or equal is not symmetric. All right, let's look at example 3. So I have my graph. So if X is related to Y by G, what does that mean? X is greater than Y. So my symmetric statement would be if X is greater than Y, then Y is greater than X. What do you think?
No.
Heck no. I mean, we can give an example, right? 3 is related to 2, so 3G2, but 2 is not related to 3 by G. Okay, so that's a specific example, not symmetric. All right, next one. So we're thinking about symmetric. So I'm going to assume absolute value of X equals Y, and I would need to be able to get absolute value of Y equals X. What do you think? We actually already have a counterexample written down.
Like the negative.
Yeah, like right there, right? -1 is related to 1 by S, but 1 is not related to -1. It can't be symmetric. It just failed symmetry for that one pair. In fact, it's going to fail for any pair like that with that situation, but so not symmetric. Whoa, that's on highlighter. I'm going to start abbreviating, not symmetric. And we can write -1 S1 1/S -1. I'm getting you used to the notation here. All right. What about example 1?
No.
Good. So it's not symmetric. Now, 2, 4, and 4, 2 work, right? If I take 2, 4, yep, 4, 2 is there. If I take 4, 2, yep, 2, 4 is there. 5, 5 works because 5, 5, and his flip is still 5, 5, but the other guys don't, right? 1 is related to 2, but 2 is not related to 1. So no, not symmetric. And that's all it takes. It's an if then, so I had the if be true and the then was false, so it didn't work, right? So it's not symmetric. Everybody okay with symmetric? Last one then here, transitive. So with transit, you kind of think of moving or transitioning or something. So here's the idea. If I have, let me switch colors, X related to Y and Y related to Z, I want to be able to combine those kind of like this, X related to Y related to Z, so that I know X is related to Z. We do this all the time with equal signs, with less than signs. We're going to see that, okay? But if I can't do that, it's not transitive, okay? So let's look at our easy examples. I guess I'll use blue for this. So if X equals Y and Y equals Z, then X equals Z. What do you think? Heck yes, that's very true, right? So equals is transitive. All right, let's check the next one. If X is less than or equal to Y and Y is less than or equal to Z, then X is less than or equal to Z. Yes, you kind of have to consider cases, you know, what if X equals Y and Y is less than Z? What if X is less than Y and Y is less than Z? What if, you know, blah, 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 but it all works out. You do get X less than or equal to Z. So less than or equal is transitive. Okay, but let's look at some others. So let's jump to example 1 first, actually. So transitive. So in order to prove something like example 1 is transitive, I would have to take every possible combination. There aren't many, but like what 1 is related to 2 and 2 is related to 4. So what would transitive need? 1 related to 4. Do I have that? Nope. So 1 not related to 4. So that's a no. There actually is another combination you could do that would work. That doesn't work. 2 related to 4 and 4 is related to 2. So according to transitivity, what would I need? 2 related to 2, and I don't have that either, you know, so. All right. I guess technically you could take 5, 5 and relate it to itself, but that's kind of silly, right? That one would work. 5, 5 and 5, 5 collapses to 5, 5. Okay. Yeah, so if you have the if statement, you have to be able to get the then statement. Now, reflexive, it's not an if then, it's just a for all. Okay. So symmetric and transitive, it is an if then. So for example, I guess if R was the empty relation, yeah, so I can write this off to the side here. That's a good one. If, well, I've used R, S, and G, let's use E, is the empty relation on X. So we're still using example 1, that 1, 2, 3, 4, 5. E is not reflexive because it does not contain 1, 1, right? So can't be reflexive. In fact, it doesn't contain any of them. But it is symmetric, right? Symmetric is an if then. If I have X related to Y, then I have to have Y related to X. But what can you tell me about the empty relation? No X is related to a Y, right? So my if is always false. And what's that mean about the statement? Always true. So this is symmetric. And it is transitive, okay? Because the if is always false, so the statement's always true. So that's kind of interesting. All right. Cool. So we're going to be using these three ideas over and over and over. Oh, I didn't do transitive for example 2 and 3. Example 2 is not going to be transitive. Again, look at our blue stuff we wrote here. Well, that one didn't work, but no, that one works. I think this one wasn't transitive. Maybe it was. Hold on. Well, let me think about it. So if absolute value of, oh, wrong color. If absolute value of x equals y, what's that guarantee about y? What type of number is it? Positive. So then absolute value of y equals z, that just means y equals z, right? So yeah, so this one actually is going to be transitive, because does that imply absolute value of x equals z? Yes. Yep, so that one actually is transitive. It's not reflexive, it's not symmetric, but at least it gets transitive. All right. Example 3. This one's also actually going to be transitive. Because remember, G means greater than. So if X is greater than Y and Y is greater than Z, yes, that does give me X greater than Z. So this is transitive. And it's because those are transitive, that greater than, that equals, that I can write those long strings of equations that I know some of you don't like, right? That I can say 2 to the n plus 1 equals 2 times 2 to the n is less than blah, 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 or greater than. I can write that string because it is transitive. I can collapse it down. Okay. All right. So let's see something we can actually do with these definitions. When we have a relation on S, okay, that is all three. It's reflexive, it's symmetric, it's transitive, it gets a special name. It's called an equivalence relation. This is a hugely important item in upper level math. Okay, it comes up a lot. So if you look at the examples we did on the previous page, example 1 didn't have any of the three. Example 2, nope, it only had transitive. Example 3, nope, only had transitive. What about our easy examples? Were either of them an equivalence relation? Equals. Equals is your most basic kind of trivial equivalence relation. It literally says, okay, we're equating everything to itself. Done. Okay, we can get fancier. Okay, so let's see that. So which, if any, none, but equals works. Okay. So let's define a relation on the natural numbers. And we're going to say x is related to y means x is a factor of y. X divides y. X divides into y. Okay. So we want to know if this is an equivalence relation. And I didn't leave much space here, but we'll do scratch work off to the side. But that should kind of give you a hint that I didn't leave much space. Okay. So scratch work. Reflexive. That means I would need for every, we'll say n in the natural numbers, I need n related to n. What does it mean by the definition of this particular R? What's it mean to be related? No, what's it say in the problem statement? That x is related to y. Yeah, so N Rn means the same thing as N divides N. Is that true? Yep. So that one's okay. We are reflexive. So far, so good. Symmetric. Okay, so I need to assume N divides M, right? Because N is related to M. And I want, what would symmetry want? What would symmetric want? Yeah, the reverse, M divides N. What do you think? Yeah, probably not. So we say, that looks fishy. Can I come up with an example where the first part works, but the second part doesn't? We are in the natural numbers though, but there is something. There you go. That one works. 2 divides 4. 4 does not divide 2. So that's another relation, actually, symbol we've been using and you didn't even know it. Okay. All right. So this will be a nice proof because it'll be a disproof, right? Proof. R is not an equivalence relation since 2 divides 4, but 4 does not divide 2, meaning it is not symmetric. Done.
You can write proof to this proof?
Yeah, normally we just say, here's a counterexample and don't call it a proof. But since it said prove your answer, I went ahead and wrote it as a proof. So is this transitive? I know we have our answer, but it still can't hurt. Let's think about transitive. So if N divides M and M divides K, does that imply, so I'm going to put a question mark over it, that N divides K? Well, let's think what this means. This would mean M is N times, I don't know, I'll use I. And this would mean K is M times J. So how can I write K? Nij. So does N divide K? Yeah, this actually is transitive. Okay. So the divides, relation is actually almost an equivalence relation. It's just not symmetric. All right. So let's look at one that actually is an equivalence relation. That'd be kind of nice, right? It's not just like x equals x. So here we go, example 5. I'm calling the relation M, and yet for some reason I wrote S in the middle. Change that S to an M. Okay. So our relation M is on the integers, and I'm going to say x is related to y if and only if x is congruent to y mod 3. What did congruent to y mod 3 mean? Yeah, 3 divides x minus y. Okay. Is M an equivalence relation? And I just told you guys it was. So we're going to need to prove this. All right. So let's go ahead. Let's do our scratch work. Oh, reflexive. So I need to take a random integer in the integers, and I need n to be related to n, but that means I need n congruent to n mod 3, but that means I need 3 to divide n minus n. So question, does 3 divide evenly into 0? Yeah, it goes in 0 times. Okay. So reflexive. Okay. All right. Symmetric. So we need to assume n is related to some m. All right. So let's write out what that means. N is congruent to m mod 3. 3 divides n minus m. So n minus m equals 3k. What is my goal here? Yeah, I want to get m related to n. So I want m congruent to n. I think we actually proved this back when we did modulo, but if I multiply this equation by a negative, I'll get m minus n equals 3 times negative k. Okay, so that's what I need, right? That means 3 divides m minus n. So m is congruent to n mod 3. So that's what I need. And I'm running out of room for transitive, so we will have to squeeze it in over here. Transitive. All right, so transitive has us assume n related to m and m related to k. So now this is scratch work. So they're congruent mod 3. So that means 3 divides n minus m and 3 divides m minus k. N minus m equals 3, I don't know, L. And m minus k equals 3j. Why not? What's my goal for transitive? Yeah, I want to get n related to k, right? I want to kind of collapse the middle away. So I need n minus k. How can I get that with these equations? Okay, even easier than solving for m. Add them together. But if you solve for m and substitute it in, you'd get the same thing. So add them together and we get n minus k equals 3l plus 3j because the m's cancel. And that's exactly what we need, right? That'll mean 3 divides n minus k. So that's what we need. All right. So let's see, we got a few minutes. Let's see if we could get this proof written. So I'm going to start over here, and then as I have space, I'm going to take up more and more space. Okay. So define, since we're short on space, we'll just say define m as above. And then you could split your proof into 3 paragraphs because we like showing what we're doing. I'm going to label my 3 parts, but you wouldn't have to label them. So reflexive. Reflexive has to work for any, what am I in? Integers. For any integer I take. So I need to take a random thing. So let n be an element of the integers. Then 3 divides n minus n. So n is congruent to n mod 3, meaning n related to n. All right, let's do symmetric. So we're going to assume N is related to M. Then N is congruent to M mod 3. Again, you can skip a little bit of steps. So we could say, so there exist, I think I used K in, well, I'm running out of room, the integers with N minus M equal to 3K. So M minus N equals 3 times negative K. Since K is an integer, negative K is an integer. Thus, M is congruent to N mod 3, and therefore M is related to N. Any questions on reflexive or symmetric before we prove transitive? All right, so transitive, we need to assume N related to M and M related to, I used K in my scratch work. Now, technically here, it would be a little more rigorous if I defined every time I'm introducing these are integers, these are integers, these are integers. But since our relation is defined on the integers, that's explicit, you know, at the beginning, it's not as big of a deal. Okay. All right, so assume that. Then we're going to skip some steps. So we're going to say by definition of M, there exist, what letters did I use? L and J. L, J in the integers with, I think I had N minus M equal to 3L and M minus K equal to 3J. All right. So adding these together, gives N minus K equal to 3L plus 3J, which equals 3 times L plus J. But that means 3 divides N minus K. Say so N is related by M to K. Again, I'm kind of skipping steps, which should be able to follow, but it also makes my proof fit in this tiny space. Okay, we could fill that in and say, so 3 divides N minus K. So N is congruent to K mod 3. So N is related to K. All right. Thus, M is an equivalence relation. Yeah, that is it. That's what we had to prove. And when you prove something's an equivalence relation, you always have those 3 parts: reflexive, symmetric, transitive. Obviously, if the problem said prove that it's reflexive, then we would have just done reflexive, right? But equivalence relation has to have all 3. Okay. And next time, then we'll get to kind of the importance of equivalence relations and why they're helpful and useful in math. So, yep, that's good enough for this time.